There is a number sitting inside a supercomputer in Geneva right now that should not exist. It is small. It is buried inside billions of collisions, and it is the reason a group of physicists at CERN spent the better part of 2 years trying to prove themselves wrong. They failed. You are about to hear the story of that failure and why it might be the most important failure in physics since 2012. Because if this number holds up, it means the rulebook you've been living inside your entire life, the one that predicts how atoms hold together, how stars burn, how your phone's processor works, that rulebook has a crack in it. Not a redesign, not a total collapse, a crack. And through that crack, something else might be leaking through. Here's the file. In May of 2026, a collaboration of over 1,000 scientists working on an experiment called LHCb, buried 100 meters under the border of France and Switzerland, published a result about something called a penguin decay. Yes, penguin. Stay with us, because the name is the least strange part of this story. A penguin decay is a specific, extremely rare way that a particle called a beauty quark transforms into other particles. It's called that because of the shape of the diagram physicists draw to describe it. Someone thought it looked a little like a penguin, and the name stuck. Physicists have a habit of naming terrifying things after cartoons. You'll get used to it. What matters is not the name. What matters is what these decays are supposed to look like on paper, according to the single most successful scientific theory human beings have ever built, the Standard Model of particle physics, and what they actually looked like when CERN's detectors recorded them happening over and over, billions of times. They didn't match. Now, before you get too excited, we need to slow down. Because didn't match is the most dangerous phrase in experimental physics. It is the phrase that has cried wolf more times than almost any other sentence in modern science. So let's rewind, and let's be honest about what we're actually looking at here, because that's what this channel exists to do. We don't chase headlines, we check them. To understand why a tiny mismatch in a subatomic decay could matter this much, you need to understand what the Standard Model actually is, and why physicists both love it and, quietly, kind of resent it. Built up piece by piece across the 20th century, the Standard Model is a mathematical description of every fundamental particle we've ever confirmed, and 3 of the 4 forces that govern how they interact: electromagnetism, the strong nuclear force, and the weak nuclear force. It correctly predicts the outcomes of experiments to a precision that borders on absurd. One of its numbers, the magnetic moment of the electron, matches experiment to about 10 decimal places. If the Standard Model were a marksman, it wouldn't just hit the bullseye, it would split the arrow already in it, and then split that one too. And yet almost every physicist you talk to will tell you, sometimes reluctantly, that they don't think it's the final answer. Think about how strange that is for a moment. Imagine building a machine so precise it can predict the outcome of an experiment to 10 decimal places, and then handing that same machine to the people who built it, and having them tell you, quietly, off the record, that they suspect it's incomplete. That's not a contradiction. That's what happens at the edge of every great scientific theory in history. Newton's laws of motion were spectacularly accurate for 2 centuries, accurate enough to land spacecraft on the moon using nothing but his equations. And they were still, eventually, revealed to be an approximation of something deeper once Einstein arrived. The pattern repeats itself again and again. A theory works almost perfectly right up until it runs into a single case it can't explain. And that single case becomes the crack that lets the next theory in. Here's why physicists suspect the Standard Model is due for exactly this kind of moment. The Standard Model doesn't explain gravity. It doesn't explain dark matter, the invisible material that makes up roughly 85% of all matter in the universe and that we've only ever detected through its gravitational pull. It doesn't explain dark energy, the mysterious pressure accelerating the expansion of the cosmos. It doesn't explain why matter so drastically outnumbers antimatter, when the early universe should have produced equal amounts of both, annihilating each other into pure light. If that had happened cleanly, there would be no galaxies, no stars, no you. So physicists have spent decades hunting for cracks. Places where the Standard Model's predictions and reality quietly disagree. Because a crack like that, if it's real, if it survives scrutiny, is a doorway. It's a signpost pointing toward whatever comes next. Toward the theory that finally explains the 85% we're missing. This is where the penguin decays come back in. The particles involved are called beauty quarks. Again, yes, a real name, chosen decades ago in a fit of physicist whimsy. And they are famously unstable. They exist for a fraction of a second before decaying into other particles. Most of the time this happens exactly the way the standard model predicts, but every so often, in an extraordinarily rare subset of these decays, there's an opportunity for something extra to sneak in. A hidden particle, a hidden force, something we haven't discovered yet, briefly appearing in the mathematics of the transformation like a shadow cast by something standing just outside the frame of the picture. Physicists call this new physics beyond the standard model, and for decades it has mostly been a phrase used in grant proposals and hopeful conference talks, not in headline results. Here's what makes penguin decays such a good place to go looking for that shadow in the first place. In the standard model, this kind of decay is forbidden from happening directly and instantaneously. It can only occur through what physicists call a loop process, a sort of detour where the beauty quark briefly, fleetingly, transforms through a chain of virtual intermediate particles before settling into its final form. Because that detour is so indirect and so rare, it leaves an unusually wide opening. Any undiscovered particle heavy enough to have escaped every previous experiment could, in theory, sneak into that loop as a temporary, invisible participant, nudging the final numbers away from the standard model's prediction without ever being directly produced or seen. It's a bit like trying to identify an extra guest at a party by looking at how much food went missing rather than by seeing them walk through the door. You never see them directly. You only see the fingerprint they leave on the outcome. This is precisely why the LHCb collaboration has been chasing exactly this kind of shadow for years, across an earlier generation of the experiment, and then, after a multi-year, multi-$100 million upgrade completed in 2023, across a newly rebuilt detector capable of recording particle collisions 40 million times every single second. 40 million photographs of the subatomic world per second. With that upgraded machine running, and with roughly a full year's worth of high-precision data finally in hand, the collaboration went back to the penguin decays. And what they found was a persistent gap between prediction and observation. Not overwhelming, not conclusive, but consistent, and showing up in more than one related measurement at once. Let's pause here, because this is exactly the moment where most coverage of this story either oversells it into physics is broken nonsense, or undersells it into a shrug. Neither is honest. So here's the actual, sober picture. In particle physics, results are measured in something called sigma, a unit of statistical confidence. A 1 sigma result is basically noise. It happens all the time by pure chance. A 3 sigma result is called evidence. Interesting, worth watching, not yet a discovery. 5 sigma is the gold standard for an official discovery, the point where the odds of it being a random fluke drop to somewhere around 1 in 3.5 million. Before we tell you exactly where the penguin decay result lands on that scale, take a guess. Given everything you've just heard, a persistent gap showing up across multiple related measurements, using the most sensitive version of this detector ever built, where do you think it sits? Above 3 sigma in official evidence territory. Below it, still just a whisper. Hold that guess for a second. The penguin decay anomaly, as of this recording, sits in that frustrating, fascinating middle zone, past the point where anyone would call it random noise, but short of the 5 sigma line that would make it an official discovery. Strong enough that senior physicists are using words like tantalizing and the strongest hint yet in public statements. Not strong enough that anyone serious is popping champagne. This is not confirmed new physics. This is a flashing yellow light, not a green one. If your guess landed somewhere in that uncomfortable middle, you were right, and you now understand exactly why this story is being covered so cautiously by the physicists closest to it, even as they privately admit it's the most interesting result they've seen in years. To put those numbers in a frame you can actually feel, a 1 in a million chance of being a fluke sounds astronomically unlikely. And it is. Right up until you remember that CERN's detectors record billions upon billions of collisions. At that scale, a 1 in a million coincidence isn't rare. It's practically guaranteed to show up somewhere, purely by accident, if you look at enough combinations of data. That's precisely why physicists set the discovery bar at 5 sigma. Roughly 1 chance in 3.5 million, instead of something that sounds impressive on its own, but would still produce false alarms constantly across an experiment this large. It's not paranoia, it's arithmetic. Learned the hard way, from decades of promising 3 sigma bumps that vanished the moment more data arrived. But here's the part that should genuinely raise the hair on your arms, because this isn't the first time this exact shadow has shown up. Back in an earlier run of the same experiment, using an earlier version of the detector, physicists noticed hints of similar disagreements in related decay measurements. Patterns that seemed to suggest beauty quarks weren't treating all types of leptons, the particle family that includes electrons and their heavier cousins called muons, exactly equally. According to a foundational assumption of the Standard Model called lepton universality, these particles should behave identically in these interactions, differing only in mass. If they don't, if nature secretly prefers one over the other, that would be a direct violation of one of the theory's core pillars. For a while, those earlier hints looked like exactly the kind of crack physicists dream about. And then, with more data and better analysis, several of them faded. They dissolved back into statistical noise, like a figure you thought you saw in the fog that turned out to be a road sign. This has happened before. It will almost certainly happen again with some fraction of what we're describing today. So why isn't this just another false alarm? Why are physicists more cautious but also more intrigued this time around? Because the current result isn't riding on a single measurement. It's showing up across multiple related channels at once, using a completely rebuilt detector, with a dramatically larger and cleaner dataset than before. It's the kind of consistency that doesn't guarantee the anomaly is real, but it does mean it's earned the right to be taken seriously, rather than dismissed as a fluke on sight. Here's your reality check. The popular headline version of this story says CERN broke physics, or found proof of a new universe. That is not what happened, and we're not going to pretend it is just because it gets more clicks. What actually happened is more interesting if you give it a chance. A team of scientists built one of the most sensitive instruments human beings have ever created, pointed it at one of the rarest processes in nature, and found a small, persistent, unexplained gap between what should happen and what does happen. That gap has not yet crossed the threshold of a confirmed discovery. It might not ever, but it is exactly the kind of gap that, historically, sometimes turns out to be the first threat of an entirely new layer of reality. Think about what that actually means for a second. Somewhere in that data, hiding behind the noise, there might be a particle we've never named, a force we've never measured directly, maybe even a clue toward dark matter itself. Some physicists have already floated the idea that whatever is subtly walking these decays could be connected to the same invisible material holding galaxies together. Nobody knows yet. That's not evasion, that's honesty. Nobody knows yet. You've probably heard the phrase, "the universe is stranger than we imagine," so many times it's become wallpaper. So let's make it concrete instead. If this anomaly survives, if more data over the next few years pushes it past that 5 sigma discovery threshold, physics textbooks will need a new chapter. Not a new book, a new chapter, wedged into the one that's already there. Because the Standard Model doesn't get thrown out, it gets extended. The way Newton's gravity didn't get deleted by Einstein, it got absorbed into something bigger, something that explained everything Newton could explain, plus the things he couldn't. That is what a genuine crack in physics actually looks like. Not an explosion, an extension. A door opening onto a hallway nobody had proven existed before. And this is where it stops being an abstract, distant story about people in lab coats and starts being about you, whether you clocked in at a physics department this morning or not. Every piece of technology sitting in your pocket right now exists because of a previous generation's willingness to chase exactly this kind of maddening, inconclusive anomaly for years, sometimes decades, without knowing if it would lead anywhere. Quantum mechanics itself started as a set of embarrassing anomalies that classical physics couldn't explain. Strange behaviors of light and atoms that respected physicists spent years hoping would just go away. They didn't go away. They became the foundation for the transistor, the laser, the MRI machine, the GPS satellite correcting for relativistic time distortion above your head right now. The uncomfortable crack usually comes first. The technology comes decades later, built by people who weren't even born when the anomaly was first spotted. Think about the actual humans behind this. Not a faceless institution called CERN, but the specific people who spend years of their working lives running statistical analyses on decay rates most of us will never fully understand. Fully aware that the majority of anomalies they chase will quietly evaporate under more data. More than 1,000 scientists from over 20 countries working across time zones on a single shared dataset, arguing in meetings over whether a particular systematic error has been accounted for correctly, whether a detector calibration from 3 years ago might be quietly biasing the whole result. That takes a specific, strange kind of patience. The patience to spend a career chasing something that might, in the end, simply not be there. There's a particular kind of professional courage buried in that patience too, one that rarely gets talked about outside physics departments. Every researcher on that collaboration knows, going in, that most anomalies fade. They've watched it happen before, to results they personally worked on. And yet they keep looking anyway, because the alternative, assuming the standard model is complete and closing the search, guarantees you'll never find the crack even if it's really there. It's a bit like the engineers behind the LHCb detector's silicon components, whose job is to build a camera precise enough to photograph particles 40 million times a second, knowing full well most of those photographs will show nothing more exciting than physics behaving exactly as expected. You build the camera anyway, you take the 40 million photographs anyway, because the one photograph that matters could be any one of them, and you won't know which until you look. Tim Gershon, who leads the LHCb collaboration, described this exact result as the collaboration's ability to make measurements in a single year that used to require a full decade of data with the old machine, meaning the pace of this hunt has just been compressed dramatically. What took 10 years might now take 1. If the crack is real, we may not need to wait another decade to find out. We might only need to wait a few more years of data taking to know, one way or the other, whether this is the beginning of the next chapter or the latest ghost in the data to fade. So here's a question worth sitting with before you scroll away from this video. If physicists confirm tomorrow that there's a hidden force out there, quietly nudging beauty quarks in ways the textbook can't explain, would that discovery feel exciting to you or unsettling? Because both reactions are honest ones. Some people hear there's more to reality than we thought and feel a thrill. Others feel something closer to vertigo, the sense that the ground they thought was solid just got a little softer. There's no wrong answer here, but we'd genuinely like to know which one is you. Drop it in the comments, because we read every single one, and it shapes what we cover next. Let's talk about what almost certainly happens next, because this is where the myth versus reality gap gets its sharpest edge. The myth says, physicists are on the verge of rewriting everything, and any day now we'll wake up to news that reality itself has been redefined. The reality is slower, messier, and in its own way more impressive. Over the next several years, the LHCb collaboration will keep collecting data with that upgraded 40 million frames per second detector. Every additional batch of collisions either sharpens this anomaly into something undeniable, or slowly erodes it back into statistical noise, the way several of its predecessors did. There is no dramatic press conference scheduled for a specific date. There is only the patient accumulation of evidence, sigma by sigma, until the number either crosses that 5 sigma threshold or quietly settles back into agreement with prediction. That process, unglamorous, incremental, sometimes disappointing, is what real science actually looks like almost all the time. The single dramatic breakthrough moment you see dramatized in documentaries is usually the visible tip of a decade of exactly this kind of grinding statistical patience. It's less like a lightning strike and more like water slowly finding a crack in stone. You don't see the crack widen day to day, you only notice years later that the rock split. Consider how the Higgs boson actually played out, since it's the most famous recent example of this exact process. Physicists spent nearly 50 years theorizing about that particle before anyone ever detected it. Decades of failed searches, false alarms, and dead ends came before the actual 2012 announcement. And even that announcement, the one that made every news channel on the planet, was itself the product of years of exactly this kind of unglamorous, invisible grinding beforehand. The discovery felt instantaneous to the public. It was not instantaneous to the people who lived it. It rarely is. So if you're waiting for a single cinematic "Physics has changed forever" headline to drop out of nowhere, you may be waiting for something that was never going to arrive that way in the first place. What you should actually watch for, if you want to follow this story as it unfolds over the next few years, is smaller and steadier. New data releases from the LHCb collaboration, updated sigma values in their published papers, and quiet shifts in language from cautious phrases like "hints of" and "tension with" toward firmer ones like "evidence for" and eventually, if we're lucky, "observation of." That's the real rhythm of a discovery in progress, not a bang. A slow tightening of the evidence, measurement by measurement. If you've watched our previous file on the double slit experiment, you already know this pattern intimately. The universe rarely announces itself all at once. It leaks out sideways, through anomalies that look small and technical, right up until the moment they turn out to be the edge of something enormous. Quantum indistinguishability, gravitational lensing, the strange behavior of light itself, every one of those started life as an uncomfortable footnote that refused to go away. This penguin decay anomaly might be the next footnote in that same lineage. Or it might quietly disappear next year. Both outcomes are genuinely possible, and anyone who tells you with total certainty which one it'll be is selling you something, not informing you. Here's the honest misconception worth correcting directly, because we see it constantly in comment sections whenever this kind of story breaks. People assume new physics beyond the standard model means something has gone wrong with the universe. Some glitch has been detected in the code of reality. It's the opposite. It would mean the universe has always worked a certain way, in full, rich detail, and we're simply, finally, catching up to seeing it clearly. The crack was never in the universe. If it exists at all, it's in our map of it. And maps get redrawn. That's not a flaw in science. That is, quite literally, the entire point of science. We want to be straight with you about something else too, because this channel runs on trust, not just views. Videos like this one, genuinely tracking down a peer-reviewed physics result, verifying the sigma values, cross-checking statements from the actual spokesperson of the collaboration, rather than just repurposing a viral headline, take real research time. Hours spent reading primary statements instead of second-hand summaries. If that kind of care is something you value, a super thanks on this video goes directly toward the research time behind the next file, and we notice every single one. No pressure at all, but if this kind of deep dive is why you're here, that's exactly what it funds. Let's close the file where every good investigation should close, not with false certainty, but with the sharpest possible version of the open question. Right now in Geneva, an upgraded detector is still running, still photographing 40 million collisions every second, still hunting for beauty quarks decaying in ways that don't quite fit the textbook. Somewhere in the data it's collecting this year, there might be the fifth sigma that turns a tantalizing anomaly into a confirmed discovery. The first genuine verified crack in the standard model in over a decade. Or there might not be. The evidence might soften the way it has before, and this particular threat might quietly go the way of earlier lepton universality hints that looked so promising and then faded. But there is one more thread in this story we haven't pulled yet, and it's the one that keeps several physicists we've been following genuinely awake at night. If this anomaly is connected to a real, undiscovered force, as some researchers now suspect, it might not just explain a mismatch in beauty quark decays. It might connect directly to the biggest unsolved mystery in modern cosmology, the identity of dark matter itself, the invisible material outweighing all the visible stars and planets and galaxies in the universe combined, that we have never once directly detected, only inferred from its gravity. If that connection holds, if the same shadow lurking in these penguin decays turns out to be a cousin of whatever is holding entire galaxies together, then this quiet, unglamorous anomaly in a Swiss laboratory could end up rewriting not just a chapter of particle physics, but our understanding of what makes up the majority of the universe itself. It's worth sitting with the scale of that possibility for a moment, because it's easy to let it slide past as just another interesting fact. Every star you've ever seen in a night sky, every planet, every galaxy captured in every photograph ever taken by every telescope humanity has ever built. All of that, combined, accounts for only a sliver of the total matter physicists believe exists. The rest has never been photographed, never been touched, never been directly detected in any laboratory on Earth in nearly a century of trying. We know it's there only because of the way it bends light and holds spinning galaxies together against forces that should tear them apart. If a shadow in a beauty quark's decay turns out to be the first direct fingerprint of that invisible majority, it wouldn't just be a footnote in a physics journal. It would be the moment we finally got a hand on something that has been silently shaping the universe since before the first stars ignited. That file is still open. The data is still coming in. And next time, we're going to follow that exact thread into the galaxy rotation curves that first revealed dark matter's existence nearly a century ago. And the specific reason physicists now think this CERN anomaly might be the closest we've ever come to seeing it directly, not just inferring its shadow from afar. There's a reason this particular case file feels different from a lot of the ones we've covered before. Most mysteries we investigate on this channel are mysteries about the past. A strange decay long since finished, a signal recorded decades ago, a puzzle history has already closed the book on one way or another. This one isn't closed. It's happening right now, in real time, underneath the French-Swiss border, as you're listening to this sentence. The detector is running, the data is accumulating. Somewhere in the next batch of collisions, or the batch after that, or the one after that, the answer is quietly being written down before anyone has read it yet. That's a strange thing to sit with. Most of what we call history only becomes a story once it's already over, once someone can look back and say clearly what happened and what it meant. This is history being written with the ending still unknown, to the physicists holding the pen as much as to you. And that, more than any single number or sigma value, is what makes this crack worth watching closely over the next few years, instead of filing away as just another headline that came and went. Until then, this has been the Reality Files. Stay curious, stay skeptical, and we'll see you in the next file.